We're going to consider Newton's third laws of motions right now, first, second, and third law of motion, and just give some good examples in this introductory videos to forces for AP Physics. So let's say I've got a suitcase in outer space, and let's say the suitcase has a mass of 20 kilograms. And according to Newton's first law, that 20 kilograms is its inertia. So it'll stay at rest or keep doing whatever it's doing unless some outside force acts on it. So let's say we have an astronaut that pushes with a force applied in this direction, and let's just say it's 40 newtons. So now an outside force is acting on this object. So then we move to the second law. And the second law says that any force net acting on an object will equal its mass times its acceleration. So for any force, if mass goes up, acceleration goes down, and vice versa. So how can we solve this expression here? Well, our force net, of course, is going to be 40 newtons. That's all that's acting on it. And let's let that equal to 20 times A. And of course, our acceleration then is 2 meters per second squared. So that's what the second law is all about. Now what about the third law? For every action, there must be an equal and opposite reaction to what's going on. So that means the astronaut is also going to receive a push back, okay, of 40 newtons. So for every action, there's an equal opposite reaction. So if the astronaut pushes the suitcase with 40 newtons, the astronaut will receive 40 newtons back. Now because we're in outer space, the astronaut's also going to move too. So the force net in this case will equal negative 40 newtons. Let's say the astronaut has an inertia of 100 kilograms, including the suit. So then I'll say 100 A is equal to negative 40. And the acceleration of the astronaut is going to be less at negative 0.4 meters per second squared. Okay, that's a negative symbol there. Okay, so we see that Newton's third law does apply very easily, and how all three of these laws relate to each other all the time. And that's really what this chapter is all about. Okay, if we look at what's going on, all right, we can bring objects down to Earth, okay, in the case of a sled here. And we have a boy, and the boy has a mass of 45 kilograms. Okay, and let's say we have an applied force of 120 newtons here. So again, the inertia is 25 kilograms. Applied force is 120 newtons. Now what kind of forces would be acting on Earth? Well, we would have a force of gravity straight downwards, and we're going to have a reaction force straight upwards on that. So the force downwards we're going to call force gravity. And of course the surface of the Earth is going to push right back up. We're going to call that one force normal. Now why is it called force normal? Well, normal in mathematics means perpendicular. So this is perpendicular to the surface of the Earth. Okay, and if we consider that there's probably some friction going this way, let's just say friction is 60 newtons here. Okay, so we see an unbalanced force in the x direction, but the forces are balanced in the y direction. And we expect the motion of this to go to the right anyways. We don't expect it to go up or down. So we can write a force net equation from this. Force net in this case would be force applied. We can label this one here force applied. And then minus our force of friction, so that we have it written in words. And this is our force of friction. And then what are we going to put in? We'll say 45A is equal to 120 minus 60. So we see that there's a net force acting on this of 60 newtons, and we'll just divide 45 into that 60 newtons to get the acceleration. So we see by what we call this is a free body diagram, where we draw all the forces on the object, and we figure out what the net force is equal to, and we divide by mass to get the acceleration. Now what about just applications of Newton's third law, a horse pulling a buggy? According to Newton's third law, every action is the equal and opposite reaction. Therefore, the sum of all forces in the universe technically should be zero. So how can a horse pull a buggy? Okay, well, we take a look at this. The legs or the hooves of the horse would be pushing in this direction on the ground. And we're going to call that Okay, force of the horse to the ground. And that, of course, would be a friction force. Now, there would be a reaction force propelling the horse forward, equal and opposite. And we can call this one force of the ground to the horse. Okay, now let's take a look at the interaction between the cart and the horse. Of course, the cart is going to feel a forward force, and this is going to equal the force of the horse to the cart. Now the horse, of course, is going to receive an equal and opposite reaction backwards for this, and we're going to call this one force of the cart to the horse. Okay, now there would be friction about this axle and everything like that. We're going to try to simplify that. Let's just say we have a friction force pulling this way, acting on the cart. Okay, so let's call this one force of friction here. Okay, and that's probably going to be ground to the cart, but there's more complex things going on there. And of course, there would be a reaction force going this way. And we can call that another friction force also. Okay, and the wheel, of course, is going to be spinning this way around as the horse pulls it. So there will be equal opposite friction forces interacting between the ground and the wheel, and also about the axle. So we'll just draw it like that. Okay. So how does anything move? Well, it turns out this force of gravity, or force of ground to the horse, is going to be larger than the force of cart to the horse. So if we look at the net force acting on the horse, that'll be force of ground to the horse minus force of the cart to the horse. Notice how the net force acting on this horse, the arrow should be pointing to the horse. That's what we're going to use for that. Okay, now what about the net force acting on the cart? Well, the force net on that one is going to equal the force of the horse going to the cart minus the force of friction. Remember, the friction force is going to be a couple of ones where you have force around the axle, force of interaction with the ground. Okay, so, and again, we notice that this is going to be larger than this. Okay, so therefore the horse could propel itself. It could also propel the cart. Okay, now if we look at what value really is the force horse to the cart, well, I'm just going to take that to the other side, and the force of the horse to the cart is equal to force net plus the force of friction. And that's kind of logical then, right? The horse has to pull this cart and overcome friction. So that must be what the cart is feeling from the horse. So that's pretty logical there, I think, if we think about that. Okay, so let's take a look at just one more example of these Newton third law pairs here. A lamp resting on a table. Okay, so let's think about this for a second. I'll try to draw them off to the side so that we don't get too confused here. So there indeed would be a force of gravity pulling on this lamp downwards, and then a reaction force upwards. What would that look like? Okay, this would be force of the earth to the lamp, and then of course the lamp is also attracting the earth, right? So this would be force of the lamp to the earth. So those would be equal and opposite. So the lamp is attracting the earth just as much as the gravity of the earth is attracting the lamp. Now what about the interactions with the table here? Well, we of course are going to have two vectors there, and I'm going to draw them over here for simplicity. We're going to have force of the lamp pushing on the table, and again that's due to gravity, and then right back at you will be the force of the table to the lamp. Okay, so right now we'll write that as this is force of the lamp to the table, and this is force of the table to the lamp. And of course, those are equal and opposite, caused by these here, okay? Now what if, now again, we're not considering what the table is doing, we're just considering what that's going to. Okay, so now let's say that there's an applied force acting on a lamp trying to move it off the table horizontally. So here we go. And let's say there's a person pushing that, and that would be a force of the person okay, to the lamp. And of course, let's say the person's over here doing that, and there would, of course, would be an arrow backwards acting on the person. We're not drawing the person here. That would be the force of the lamp to the person, right? So imagine a person standing here. Now remember, there's friction between the person's feet and the ground, so the person's probably not going to move. So this lamp is going to begin to slide to the right. So there would, of course, then be forces going backwards, the interactions between the lamp and the table. And again, I'll draw it up here so that we can see it. So again, we are then going to see that there would be a force of friction. Okay, and that force of friction, I'll do force FR like this. That's going to be table, okay, to the lamp. So this lamp's trying to slide this way. The lamp will feel friction force that way. And of course, there would be, in this direction, okay, a force of friction, lamp to the table. So what that means is, if I'm pulling this lamp in this direction, there would be a friction force between these two, trying to make the table move to the right also. Now, whether or not it moves depends on the interaction between the friction and the floor. So that's all of the forces considering the lamp involved with the table. We're not going to get anything else involved with this photo here. We're just looking at the lamp interactions. So once again, we see that all forces balance out with each other. Okay, these two balance out, these two balance out, these two balance out, but you have to remember when we look at the net force acting on the lamp, when we're trying to move it to the right, okay, that's going to be force net acting on the lamp will then be force of the person to the lamp minus the force of friction, okay, table, okay, going to the lamp. And that's considering all of the third law pairs. Now again, the force of the person to the lamp, if it's greater than the force of friction from the table to the lamp, then we know that this will accelerate to the right. Now that's when we look at all third law pairs. We're going to simplify, okay, this object's free body diagram from now on. And let me show you what that would be. We'll draw a dot to represent the center of mass of the object. We're going to draw force gravity downwards and a force normal upwards. So this is force gravity and this is force normal. Okay. Then we're going to show to the right a force applied and to the back a force of friction. So this is going to be known as force applied and this is going to be force of friction. So this equation then becomes force net equals force applied minus force of friction. So this is typically what we're going to do with our free body diagrams. This more complicated version is just showing all the Newton third law pairs of all the interactions of everything around. So we're typically going to just draw a dot to represent the object, put the forces acting on the object, look at the net force acting on the object, and then solve for the acceleration. Okay, that's it for our introduction for this chapter. And look forward to more videos coming soon.